In this demo, we will show how a deep learning pipeline can be executed on a hybrid HPC cloud infrastructure, OpenDeepHealth, which is available at the University of Torino. We will use the deep learning libraries and tools developed in the DeepHealth project. The pipeline's goal is to train a model to recognize lung nodules from chest CT scans. There are great expectations to unleash disruptive innovation across the health sector thanks to better exploitation of the health data and artificial intelligence and machine learning. The European DeepHealth project aims at contributing to such an epochal change, exploiting in particular biomedical multidimensional images and state-of-the-art AI based on deep learning methods. The DeepHealth project targets the development of a European Computer Vision Library (ECVL) and the European Distributed Deep Learning Library (EDDLL), coupled with advanced programming models and tools optimized for parallel execution. DeepHealth exploits the usage of AI tools thanks to several software platforms, including the University of Torino's OpenDeepHealth platform. It supports the training and inference of AI models on hybrid cloud HPC infrastructures. The key technology underneath the transparent deployment of AI tasks onto multiple infrastructures is StreamFlow Workflow Management System. Also, the University of Torino implements a pilot hybrid cloud HPC infrastructure, which is composed of the Occam et Unito HPC modular cluster and the HPC4AI private cloud. Occam et Unito exploits bare metal virtualization based on Docker containers. HPC4AI implements an OpenStack cloud, enhanced with the deployment as a service. It enables the deployment of segregated instances on the OpenDeepHealth platform, which makes possible to securely manage critical data on a shared infrastructure. In practice, the OpenDeepHealth HPC component, Occam, is equipped with the DeepHealth Toolkit Docker containers on bare metal. The cloud component, HPC4AI, is a multi-tenant Kubernetes cluster with the DeepHealth Toolkit containers too. The StreamFlow workflow management system allows orchestrating the execution of different tasks on both the components. StreamFlow allows the declarative description of possibly many multi-container environments to be used simultaneously for the execution of workflow nodes. Workflow description specifies the application steps, while the model description defines the target infrastructure's capabilities. This demo is devoted to one of the 14 use cases defined in the DeepHealth project, namely automatic lung nodule segmentation in chest computed tomography scans, whose goal is to train AI systems to recognize lung nodules using chest CT scans. The dataset has been provided from Città della Salute Hospital. Images have been anonymized and radiology experts manually segmented the lung nodules to prepare training. The DeepHealth libraries, both EDDLL and ECVL, are used to develop training and inference by means of Python scripts. ECVL manages input and output data formats, and EDDLL is used to define a U-Net neural network for training and inference. We will demonstrate how the pipeline can be automatically executed on an OpenDeepHealth platform, performing the training and validation steps on multi-GPUs node on Occam and the testing phase, the inference step, on a CPU node on the HPC4AI Kubernetes cluster. This is the overall control flow of the pipeline execution on the OpenDeepHealth infrastructure. StreamFlow will take care of orchestrating the pipeline execution based on the description of both the pipeline and target infrastructure provided by the streamflow.yml file. The pipeline is described as a workflow of two steps, training and inference, while the architecture is defined by means of models, a Helm collector of the Kubernetes cluster, and an SSH connector for directly launching the Dockers. The expert user on his own terminal launches the StreamFlow process. Now the training is starting on the remote multi-GPU nodes on Occam. The user may check that the actual node is working as expected looking at the GPU's monitor. We can see that there is memory allocated and the process is started, running simultaneously on the 4 Tesla V100 GPUs. Now we're going to accelerate the process because the training, of course, will last for hours on our dataset. So let's speed up this process. And now we can see that the training steps on Occam is completed. StreamFlow is transferring data from Occam to HPC4AI cluster and deploys the inference step on Kubernetes. We can check on the Kubernetes console that the pod has been deployed and is pending while the actual inference process starts. Again, we need to skip this part for the execution due to the demo time restriction and jump to the last step. Finally, the inference step is completed and we can take a look at all the statistics. Here is the user browsing on his own machine where he can have a look to some images provided by the inference and check that the nodules have been correctly segmented. Thanks for the attention.